So we spoke a little bit on the foreground handling. That was how an interrupt works. We try to understand latency, interrupt responses, interrupt recovery, deferred service routine, ISR processing time, non-maskable interrupts. Not really that we spoke in length about non-maskable interrupt. It's very easy to understand for all of us. You all guys being from electrical background, that interrupts which cannot be controlled and once arrived can only be feedback or delayed, but will always arrive. For example, sudden power loss is a reset is a very good example. Now today in real-time OS we'll talk about the another thing which is in the background process. So system can be always interrupted, absolutely. But while the interrupts do not arrive from external world, there are some other jobs which you do on behalf. And it's a combination of both. So, you take some, input and then, while processing, you do things in background. So processing work usually is a background work. And let's see how tasks can enable them. So often that part is referred as background handling. And background handling can be thought as task-based handling. Sometimes you also have notional difference between process and threads. Usually in real-time OSs, we say any job which is assigned to do some job is or work assigned is a task, and task is the smallest possible breakdowns work structure. Okay, so let's start with that how OSs or various real-time OSs try to manipulate or help using tasks. If you look at this red dotted background, this one, this is how we're trying to depict as a kernel. And we're trying to see that there are a lot of tasks, application tasks. Okay, and they are interacting with some kind of an interface. Besides, apart from application, you have some external interrupts, excuse me, with clock or timer interrupts attached. They usually process IO and interrupt. And now there is some kind of initialization code on the right hand side that's also connected. And then you have the one which manages time of the processor, task scheduler. So it decides, which task to run next, and so on. So these all are achieved. It's pretty difficult to, implement these stuff. So, real-time kernel from commercial backgrounds, they provide easy mechanism to make use of this, because ultimate objective of a real-time kernel is to get utilized by apps. So how they perform is by providing a set of services. And the system services usually is a part of API interface. When I say API interface, it's like a function you can think in C++. Okay, usually most of the OSs which you see in this world are very popular and they are written in C. So it's an absolute, acceptance that C is the ultimate language for writing system programs. Now, that's why. So I was saying that, as a programmer, if you have to design some application, one of the easiest way will be to learn a set of functions provided by that kernel. And unfortunately, real-time kernels are very specific. So you may not be able to find one function which is going to be linear across all real-time OSs. What I mean by this is, if you used an API to create a task in VxWorks that may not be compatible to create a task in Linux, or that may not be practically feasible to use in QNX and so on. So there is a, this uneven API interfaces, which either you need to mug for systems performance, or another layer of API, which is POSIX interfaces. I spoke about POSIX. Does anybody remember the full form of POSIX? Any acronym? Let me see the chat box. Yeah. So is the chat. I can't see them. All right, I'll leave it. So once again, I repeat for you, POSIX stands for portable, P as in portable, O as in operating system, I as in interface, and X as in Unix like machine. So if you ever had a set of API and which is POSIX compliant, then most of the Unix like machine will be compatible to it. So there are a lot of real-time OSs who are real-time POSIX compliant. For example, QNX or VxWorks or PSOS or OnTime, all are trying to Linux. I mean, embedded Linux, Monte Vista Linux, Timesys. They all are really trying to be at par with POSIX, right? But otherwise, besides, there will be some unique, API which you need to really work on. Now, what these APIs will usually contain is these kind of management. You will have task management, or you could have to have memory management for those tasks. Or sometimes, you want to use some peripherals connected to them. So you may have a lot of IO management, naturally timer management, a lot of other things like security management, file system management, and the list goes on and on, just like an OS, right? Now, if you want to just try and understand what could be there in a task manager, let's see it. So now we are trying to give you a small sequence that, every application, whenever you write, okay, the application will always try to interact not directly to the hardware. So this is not the root. So, so to the hardware. This root doesn't exist. An app will always be making a call to system calls, and either through some libraries maybe, and then on behalf of you, there are certain codes provided by the kernel. For example, to create a task, or suspend a task, resume a task, delete a task, set the priority for the task, remove the priority of the task. Similarly, if you want to have some kind of timer installed for a task, you can create timer, you can sleep the timer, and so on. If you wanted to perform some IO activities, you can open a device, open a file, read from a device, read from a file, and so on and so on. So there is a list goes on and on, like Linux-like systems have roughly, 350 plus APIs like this, system calls. And, this is always growing in number. Usually a Unix used to have 70 plus classic system calls, but it's been extended over a period of time in the last 40 years. Okay. So this is a very natural way by which you will, interact in the system. Now let's understand a little bit more about the task. As I said, you can think of any, part of the program as a function or a mini small program that thinks that it has the entire CPU to itself. And every task in, preemptive kernel is assigned a priority. And it has its own set of CPU registers and its own stack. If you remember, I spoke about that in preemptive kernel, each task must have its own dedicated stack, right? So that's the thing which is there. Now, the most important thing is, the state machine, and task can have a lot of states, so every operating system again will have certain, defined term for their tasks. Like some of the, general terms used here is dormant, ready, running, waiting, and even ISR. So when we say ISR, it refers to the interrupt state, or it's, processing interrupt state. Okay. Some diagrammatic view of handling the tasks can be seen like this in the states. But before that, I will also like to see that, how does the real-time OS, handles the tasks. If you look at that, usually there is a representation of a task. So there is a software data structure which we use. So, in C, you can think like a struct, which is used to represent a task. And usually these tasks are referred by task control block. So task control block, okay. And if you look at, the relationships, there will be something like this, guys. A task control block will be having a program counter, it may have task status, and it can have task ID, a lot of contents of the register. You can also think of, that it holds the reference for the next task which is going to run in case if it's available, and so on. From the diagrams, you can think here, let me draw this, that there is one program, and for one program there can be multiple set of tasks, and for each task there can be certain stacks. So I think I should do like this. This is the stack till this n stack, So for every TCV, if I think that this is one of my tasks to do some logging, this is one of my tasks which can do sensor processing, this is another task which does a correlation. Okay, so for all these tasks, there will be separate stacks. So you can think of, if we have allocated certain stacks with even different size or same size. So maybe, this is given to this. You think of this is given to this. And this is given to this, So by having this, we can think, there are 3 tasks. So this can be, say, TA. This we can think of TB. And this we can think of, say, DC. Doing different jobs. And this is the stack. Okay. So that becomes this stack uses something like this. So you will see that, if you want to create certain task, like, though we have a case study of VxWorks, they have, APIs to, reserve the amount of stack you require for a particular program. Okay. Or diagrammatically, at least it will. Now let me come out to a diagrammatic way of you saying that, two-state model, so simplest model you can think in a kernel, that a task can start himself or enter, okay, and then it may have, it may be running, okay, so it starts here, then as of now it is not running, and then there will be a dispatch. So from dispatch, you can think it is running. Second, it could exit If not, it can pause. And as a matter of pause, again, it is not running. So, a non-preemptive kernel kind of a thing. You can also add preemptive model in the same thing. Now, a software representation in diagram that we need to design a queue, right? This is a queue. And each task can go and sit in this queue. So, we can either decide the order, or if it is a preemptive kernel, based on priority, they will be sorted and placed in the queue, and so on. Now, the dispatcher is a function via which this program will be given in CPU, assigned. So the content of these task control blocks will be copied to the processor till it exits, one option. Second is, it is waiting for some kind of an IO or activity, others goes pause. Once again, it starts from the queue. So it's like a cycle, which could keep running for a set of few tasks in your system, something like that. A little bit more, extended, like a task can be shown as ready, and then from ready you can go to running, right? So this becomes one. From running, you could be blocked. From blocked, you could also become ready, or you could also be running. Depends. And then, if there is any higher priority task, that can again become ready. And this could be a cyclic process again from here. So from blocked, it could be ready, or it could be running. But OSS provides control where you can, even delete these tasks which are in the block state or something. So its state is of no meaning from there onwards. A little bit more extended. This is from Mikram, OS Microcross or US. They write it as mu. I'm sure you're aware. Mu cos COS, because, and right now the version running is 3. Okay, so that's the location. So here is trying to say that you create, then you become ready state, and from ready you get a dispatch to you go for running. From running, more likely is that you get interrupted. So you can think of that's one of the option, 3.1. Another option is here, 4.1, which you can think of, block or suspended. From running task, it could be blocked for some reason. For example, it is waiting for a semaphore to arrive, waiting for a message queue, pending messages, okay, or it is waiting for a keyboard, or so and so on. So it's waiting. And then from there, it can go to again resume, and then again ready and go ahead. Similarly, in 3.1, interrupted, from return from interrupt, it could raise back the program to running, and so on. So something like this. It could also be that you dispatch and from running timer is run out, so you can go back. So that could be, just giving one sense. And then you could also get deleted in the program. So program is no longer in the system. So you can think of these kind of notional state machines, which is used by various real-time OSs. Okay. As a case, you can also browse on internet and try to find out your different OSs. Like you can take down MicroVitron, VxWorks, QNX, okay, as an example, and try to find out their states. What are the different kinds of states there? Okay, guys. This is more of a detailed description that every task control block which you have. Okay. So here, this is my TCV, and it has a forward link for other task, and it also has a backward link for some other task. You can think of one more task control block like this. Let's see. Maybe over here. You can also think notionally one more task. This is also your D, C, B. So, so that you have a track of, okay, this is one task, this is another task, this is another task, all the three tasks. And needless to say, this is stack pointer and stack segment. So it is pointing it to one stack, so it's a stack block. And every task will call some functions of a function pointer will be pointing it to actual work which you want to do, code of your task. Then it may relate to some shell, some return values, some state pointers, the task behavior, the priority of the tasks, and so on. Now to maintain these tasks, when you saw the links and all here, so I said this is forward link and this is backward link. How do you maintain these tasks? So there is something which we call as a queue. So there are several types of queues. Okay. Usually, they use various data structure to implement them. Simplest could be doubly linked list. But there are a lot of different ways by which queues are created nowadays. Okay. So there are several kinds of queue. And usually there are three queues which are very popular. One of them is referred as the ready queue. So we can think it is a ready queue. The second one which you have is device queue. And even they maintain await queues, pending queues. Something like this. So ready queue is nothing but, it will have a set of all the tasks which is going to be run, yet to be given to the CPU. Device queue is the one which is connected to some kind of a device, list of device pending for their services on an IRQ line. Wait queues are the tasks which are waiting for some signal or event to arrive for their execution. Something like this. Now, one of the very frequent thing which happens in every real-time application is that application comprises of a lot of tasks and tasks keep switching. So it is like, context switching or a task switching. And this is an overhead. So a lot of real-time operating system do not like to store the entire task and then bring them back, again bring it back. And hence, they use thread-based mechanism, like so that, least amount of information need to be shared and brought back, because it improvises and increases the response time of that application. So that's one of the things. So it's always good that we try to understand certain application and tune our least registers for it, because the more and more registers you will have, higher will become your overheads. So everybody wants to be very careful while designing a task control block, that you don't over exhaust beyond the feature. So choosing an optimal set of element which is required to do the job, and that is from the design perspective, guys. As an application programmer, you really don't worry on that side. If you're an embedded application developer, then you just want to know that what functionalities are available, and you should have a very good programming technique. You should have a very good, strong reading ability and visualization techniques. By that, I think you can write or program real-time OSs. It's very simple, man. Yeah, some more details on this page, that what kind of information do you want to, store. Naturally, the first one everybody knows. Second and third, you can think. Co-processor register, in the sense you can think of FPUs, floating point registers. You can also think of something like multimedia extension registers, and so and so. So there can be a lot of such, specific information which may not be a part of a task control. So these all things may be occurring overheads. Like you want to create certain pages which are in the memory and store them in register for a speed. Certain special variables you need to have it for a task, without which a task cannot function very well. Right. So all these things can actually create some overhead, which I was talking. And it's important that you know that. Now, as you know, decision making is one of the very hardest job, and task scheduling is one of that aspects. And scheduling inserted when the queue is ready, and there are several policy used. Some of the very popular ones, which everybody must have been, hearing or maybe gone through in your optional or in your engineering colleges, are like these, first come, first serve, round robin, priority based, sorted job first. But the challenges are there. In real time, you'll have real, challenges for having deadline being achieved. So based on real time characteristics, we have two types. One is rate monotonic, and one is earliest deadline first. And unfortunately, earliest deadline first kind of schedulers are not available by default, because it has to be edited and tuned for an RTOS. Usually people hire doctors for event-driven based, scheduling to be written or to be amended ways. Now, sometimes you should also know that, how do you set up the priorities? So one of the easiest ways is take a number and assign it, which is true. But it's always good that you know and weigh the criteria, whether importance is the criteria or whether utilization is the criteria. Usually, utilization becomes the criteria because you want the CPU to be completely well used. So what you do is you want to see the CPU usage factor for assigning the priority. But sometimes it's like the deadline, irrespective of the amount of CPU load you take or time you take, if this task does not run, it can lead to a catastrophe or disaster, right? So in such scenarios, you should look for dynamic scheduling, and they're really very hard here. See, these are some categories in diagrammatic way, and we are trying to show that these are the ones which are more often used. Another example. This is round robin with preemptive. So you can see several tasks running over here. Actually, we have task 1 running. Then we have task 2 running. Then we also have task 3 running. And then we can see there's a preemption also coming up. So that's also trying to, run here, which is T4. So T1 runs for some click, then T2, then T3. Again, T1 gets the chance, so it runs. Again, T2 gets the chance, which it runs. Now, here is where another task has come in the system. which is T4, and its priority is higher. So first it executes, and then T2 starts. So you can think of an interrupt arriving here, ISR, and that leading to help desk. So round robin with preemption is something which is very, very popular in POSIX-based, system. So of course, sometimes people may prefer you asking that, do you know what is preemption? One of the simplest ways is you take the number of lower priority and higher priority, and you start the answer with that. Let's assume a use case that there's a lower priority running on a CPU, and if a higher priority task comes, then kernel gets involved in, deciding the higher priority task to execute. So it preempts the lower priority task. So kernel gets involved, and it happens dynamically. Its behavior is built. Kernel source code is built for this lookup, and then hence preempts the running process or a task. This is a purely priority-based preemption that T1 is being preempted by T2, T2 is being preempted by T3, and this is all, it is based on the higher priority. Now this task till it's complete, now T2 till it completes, then T1. So what it is, the most important task, this is the most important thing, or the highest task will always get the CPU first. Always it will get attention. Once it is done, then the next second highest priority task. So you can think of next high priority task running over it. And then followed by that, the least priority task. So that's how you actually move around these kind of priority. Now among these, we'll say earliest deadline first. The logic is very simple. As the name suggests, earliest deadline first. It means if we have two tasks, we'll find that currently which task's deadline is going to meet faster. So I think one simple example you can think is here, we'll take, assume that, we have a T1 task and it takes 20 seconds for execution. And there's another task called as T2, which takes 40 seconds for its execution. Now what we do is we put a deadline over them. So we'll put a deadline as, say, 90 seconds. Okay, and we'll put this as 70 seconds. So by looking at this, what you're going to understand is that which is the task among these two which is quickly going to approach its deadline. Of course, T2 is 40 milliseconds. So let's draw a diagram here only. You think, that if T1 runs, if T1 is greater than T2 in preemption, T1 runs for 20 seconds. And then T2 runs for 40 seconds. Okay. We aren't handling any interrupt. Suppose one interrupt arrives, whose time slice is, say, 20 milliseconds or 15 milliseconds, or second in this example, if we have taken. You will have a crash in the system. We are taking a best case where there is no interrupt, but unfortunately, you will have events. So every time an event arrives, it will be a crash. So one interrupt itself can cause problem. If we take a base, interrupt latency of 15 seconds in this example, guys. Okay, it may be microsecond or milliseconds, but here in this example. naturally miss out the deadline on this. Okay. So one of the easiest thing, that every programmer will start thinking is, let's make every task as a, function as a task. So if I write 500 function, all the 500 function can be referred as a task, and that's worst. There are huge guidelines to create a task. It may have a lot of collection of software functions. And typically such functions which has to be repeated again and again, they cannot be a part of task. Let it be as a part of library so that it could be reused, Otherwise, operating system execution for each task will end up overwhelming the capacity. And that's not good. Okay. So just a summary page for choosing the priority: offline, static, online, dynamic. As I said, the criteria for urgency and criticality is chosen. And in this trade-off, often urgency is chosen over criticality. Because most of the practical systems which we see around us are soft real-time systems. But if it was a hard real-time, these stuff will change. As you know, problem with the hard real-time systems are one. You have to be very careful that each separate task should have separate deadlines, because one missed deadline is a failure of the entire real system program. The purpose of real-time itself is defeated, right? Hard real-time system. Remember, no? Fail to respond to one single event is considered as the complete system failure. So we conclude that, one such, scheduling mechanism is not good enough, isn't it? So we need to have a combination. So every real-time OS, will provide a combination of all these. Some will provide you by default preemptive, but RR will be there. There will be a mechanism to lock the preemption so that it's disabled and you can get into non-preemptive kernel and so on and so on. So I can conclude you guys saying that there is no one such algorithm which will fit all, and they range from a combination of whatever we spoke, or maybe a little bit more customized scheduler for that typical application. Okay, I've given you some small example here. pthread API summary will anyway take these working examples in a while from now, maybe on the Ember Linux view. And here, these are some ways by which one can create threads like pthread APIs. I'm not asking you to get mug up, but just be aware that, okay, pthread is a set of standard API which helps you to create threads and manage those threads in your system. And good thing is, if you know this, most of the Unix provides this. Most of the real-time OS are compatible to. Guys, so now what we do is we take a little bit of a break. Okay, let's pause for a while. And then, in another 5-10 minutes, we'll start. Is that fine for you? All guys? You guys can hear me? I don't know. Hello? So let's take a break, guys. And we'll join in another 5 to 10 minutes. Okay. So guys, I was on a mute. I was trying to tell you about there are two ways to communicate. One is a direct communication and one is indirect communication. In direct communication, there is no intermediate storage, no memory used by kernel for talking to each other. In fact, kernel does not get involved in doing this kind of. The simplest mechanism, there is a sender task, which I have placed it as S, and a receiver task on the right hand side. Sometimes sender tasks are also called as producer, and sometimes receiver tasks are also called as consumers. So I should have written C like this: consumers, producer and consumer. Now, a sender must know the address of the receiver task and vice versa, receiver also. Now, one more thing is, because sender has started sending the data, sender cannot do any other job. So if it is one, it cannot do the second job. Okay, it is very tightly coupled. So till its work is done, it has to be hooked. So very real-time task, which doesn't have much dependencies, can use. On the other hand, the most practical use or pragmatically used system is indirect communication. In indirect communication, what happens is you will have a common buffer, guys. Okay, so you can think of that a common buffer is used in the system. This is a so think that this is a common buffer. Some data are here. You just think like this. I'm just trying to color it for appealing. This is your buffer. And now we can take one task here. And another task here. Of course, different situation. You can have multiple receivers also. Just trying to notional show it. So this is your producer and this is your consumer. Or you can think this is a sender and this is a receiver. So a producer can write here to the buffer, say A, and a receiver can go and read something from it. Well, this is doing, it can write and producer can also do some other activity. Which is okay. Do other work. But the same thing is not feasible in the direct communication. Similar, receiver also can come and see if there is no data, it can come back later. Okay. If it is here, okay, it's not there, it can come back and it can do some other jobs. Okay, something like that. So that's an advantage. So it is need not to, sender task need not to wait for a receiver task to complete enough. I'll come, it's also called as pub sub, publisher and subscriber. So I'll come, I'll dump the data on a particular buffer and walk off. Again, somebody who wants to receive will come and he will subscribe the data and go. Something. It's a very neatly implemented mechanism. Now, you can see these are the mechanisms for indirect communication. So one can ask you, okay, what are the different examples of indirect communication? One of the very common ones I have listed over here. Every real-time OS has this: pipes, message queues, shared memory, sockets. All of them are there. The first three is used for native communication. Means a task communicates within that OS, within the device. Socket is a way by which a task can communicate across other devices also. It means on the network, if there is another device connected, so you can think of a client and a server tier architecture, where client can become, like a consumer. So it will send a request that I want this information, and server is the one which will produce that message and send it to you. This is a very prevailed method in most of the real-time operating system. Socket is a very nice and proven method by which connected systems can work. Okay. And on socket, there are a lot of other frameworks which is built. For example, you can look for a remote method of invocation or RPC, remote procedure calls. You have Open Binder, which is built on top. So you have something like CoAP, Constraint Application Protocol. You have something like MQTT, so message queuing, telemetry, transport layer protocol. So like this, there are a lot of data, DTS, a lot of application specific protocols are available, dbus, all built on sockets, and they do a wonderful job in allowing processes to communicate from not only native different runtime environment, but also across different devices as such, Some diagrammatic way of you explaining pipe. Just an example of pipe is a very good example of half duplex communication. Half duplex means either read or write at once. You cannot perform both of them at once. Either you can read while you're reading, or write cannot be performed. It means you have to close the other end. While writing, you have to only perform writing. You cannot read, you have to close the other end. So that's why a pipe is a very good example of serial communication. For example, keyboard is an example of a serial buffer. This is strictly serial buffer. You cannot perform any random read write. So it's like, if one wanted to read ABCD, okay. So in ABCD, you cannot read D without reading ABC. So that is an extremely strict serial buffer. So pipe is a very good example of that. So for slow communication, for IO multiplexing, and IO multiplexing in the sense multiple descriptor can be watched by using pipes, and also performing synchronization techniques, like a very high speed device can be connected to a low speed device like pipe for synchronization. So these are some strong uses on pipes. Excuse me. As I'm trying to, tell you here, right? So on the operation on pipes, I think you can think it is a strictly serial buffer. Okay. Another way is message queues. So as the name says, message will be queued in a FIFO order, first in, first out, and will have some tagging mechanisms also. Okay, you can see diagrammatic. This is a sender which is trying to queue certain messages in a particular queue. So every queue will be having some unique ID via which you can recognize. So if receiver wants to read that, he should know that key. So he'll go to that ID, get the file descriptor, and then it will try to receive the messages. Something like this. Sender, what it does, it keeps producing the messages and it keeps placing this. A lot of APIs are there, like message queue, message get, message receive, and all, or MSGQ send, MSGQ receive, MSGQ. Like, why I'm saying it, these are some mugged up APIs from me from VxWorks, QNX, Iridium Satellite, and all those things. Which project we were working on, almost 20 years. Another very fast way of you communicating is shared memory. Now, the problem with the pipes and message queues are, once you read the messages from there, they are no longer available. So if you have multiple tasks who wants to subscribe to the same message, you have to end up creating n copies. That can be a little bit heavyweight or overhead on your machine. This is where shared memory can be very good. A lightweight mechanism by which you can have data which can be shared across two tasks and can be a fast way of communicating. However, it comes with its own trait. If you have a shared memory, then you have the data retrency problem, right? Because in a preemptive kernel, one task while it is doing something on this shared memory, other can come and use it for its own purpose. And higher priority task can easily disrupt the low priority task running in a preemptive kernel. Hence, you need to provide some kind of a synchronization mechanism or a race condition handling. Usually you do it by using semaphore or event counters. Okay. So resource is the general term. So any object like memory, variable array, socket structures, devices, IO configurations, these are a very good example resources. But shared resource means it's used by several tasks and can be used simultaneously. And there must be an exclusive access or a mutual exclusion provided to, okay. I mean, provided to all the tasks, or maybe to give its access across the shared resources. And naturally, semaphores are represented diagrammatic like this. And that's what they say, that there's a concept of critical section. So what do you mean by critical section, guys? A section which must be mutually exclusive. This is a section which is very critical. It means this is the place where both the task or end task wants to make use of it. And if it is simultaneously on a multiple cores, it can be a very bad hit. Hence, there must be a way to mutually exclude them. Well, a very popular interview question is, guys, do you know what you mean by reentrant code? So, a shared code must be reentrant. You can easily say such code which will be shared by multiple tasks simultaneously, but without having any side effects on their own operations and data. So every shared code must be reentrant because very efficient mechanism. One function and multiple tasks can use. Otherwise, you have to keep binding this definition as a copy for every task. If you have 50 tasks, you will end up having 50 different copies of the same function. That's why by making all these functions as a library and a reentrant, it becomes very, very easy. Like in C, your printf, scanf, and all are a very good example of a reentrant function. It means multiple application uses them. You print hello, I print hi, somebody prints bye. So it cannot be that for you it will become bye, for me it will become hello, and for somebody else it will become hi. How it happens is naturally because of this reentrancy aspects. Diagrammatic way to show that multiple tasks are trying to use a shared resource. My function is a common function. As you can see here, this my function is being called here. Here also this my function is being called here. So this is an example of a shared code. How do you control this simultaneous writing? They say semaphore. So there are, you can think of it as a synchronization tool or just a variable technically, okay, which controls the critical section or a non-reentrant code. So what do you mean by non-reentrant code? Such code where you are using the global variable data in a non-atomic way. Okay, it means more than a couple of cycles is going to be consumed, and that can cause interrupt. Now there are three types of semaphore. Again, this is coming because of VxWorks terms. Worth knowing it. Binary semaphore, counting semaphore, mutex or resource semaphore. The fastest semaphore is the binary semaphore, but it cannot maintain a track of how many times the ownership was awarded to which tasks. Counting semaphore does that. It maintains the multiple instances of a guard. for an application. But unfortunately, counting semaphore does not allow the control for priority inversion, one of the most popular bugs found in every real-time OS. Okay, so mutex is a semaphore which actually addresses the priority inversion problem and provides a solution to priority inversion by providing priority inheritance protocol or in the favor of any other protocol. As I said here, these are some counting. You guys can have a look as a PDF when I give you later. Know the meaning of PIR. Priority inversion means the inverted priority. It means a lower priority task is running and a higher priority task arrives and it wants to use the same resources which currently lower is using. Hence, that's an example of bounding, right? So bounded priority inversion is happening. That a lower priority task was bound to wait for the higher task to get completed. So how do we solve it? By using priority inheritance protocol, which is PIP. So what it does, as the task is occupied, its priority is provided to you. And once you are done, the old privacy is assigned back. Hence, you achieve inheritance. Another option by using it is using priority ceiling protocol. Okay. But before going there, I'm giving you a list of APIs. Like if you want to use message queues, you can use mq.h, mqdt. This is RTOS for real-time OS, and POSIX API. This is the list. Sorry. So that's a set of API. Now, while using the semaphore, sometimes you will have a condition of deadlock. Deadlock is a very embarrassing scenario, guys. And it's like, you have attended a lock, but you're not freeing them. And hence other tasks cannot also claim it. And that can lead to a deadlock, guys. So we have to be extremely careful that, one must follow a very obedient scenario that, if you have acquired the lock, you must free them. Otherwise, it may not be provided to any other task and system can go completely, vulnerable from there onwards. So deadlock is an unsafe zone. We must carefully handle them. Also, some things apart from this which you should look for is, the timers. Timers becomes very important, and there will be onboard computers based chipset timers and clock, and there will be some auxiliary clock for additional drivers which you can write it to manipulate for separately. Like there's an example of system clock ISRs trying to perform some bookkeeping, keeps incrementing the time clock and keep updating the delays of the time in and out. And also operations needs to be rescheduled. There's a small example of VxWorks where you can see, it's like always VX86 is a variable which is a 64-bit, keeps rolling to the power 64, quite long, but yeah, that's how you maintain some kind of interface. You'll have croutine to execute the delay, and if the watchdog timers expires, you can think of application being warmed or alarmed with it. So just like an ISR registration, you perform the same thing here. There are some surveys on RTOS like links.com, windriver.com for Iridium satellites, Mars Pathfinder, windriver.com, QNX on shared memory big machines, VRTX from Mentor Graphics, and even Symbian old, you can go to Android, iOS, and so on and so on. I placed a very quick case study, guys, that all is what you learned, right? As a standard, VxWorks operating system was a leader to perform these kind of services. You can see it's trying to diagrammatically show that it has a fantastic kernel with an application having heap memory, certain semaphores, message queue systems like Q and Qt, a lot of task creation ability. It's scalable, configurable. It is a flat address. Flat address means entire address belongs to you, kind of an implementation. Okay. The WindRiver kernel is portable for 20 plus different microprocessor families, huge. Now they say claim it to be 80 after Intel acquired it. Very scalable. It means you can decide how much features you want. So they will ship only what you need, not everything. And it is damn deterministic, high speed Wind microkernel. So that's a another thing which you can think. And this I have already explained in diagram that everything has been used as a part of scalable. Everything is there, whichever you want. This is an example of how an OS can be scaled up. You can make a microkernel roughly around 5 kb with VxWorks, or a standalone without any network kind of a feature, or network OS within 100 kb. Entire with some basic file system, you can make it to 250 kb, and equipped on a flash within half a meg. So half a meg, entire OS is almost ready and running, which is awesome. It's perfectly fit for real-time applications. Now what you need is certain IDE for programming them. And there are two kinds of IDEs. This is an older one, classic. It is called as the Tornado Foundation. On the left-hand side, what you see is a host-related tools. On the right-hand side, it's a target-related. And there are several ways by which a target server will communicate. Like you can use an Ethernet for communication over here. You can use a serial line. You can also use on-chip debugger like JTAG, BDM, Nexus, or certain custom can be created like, for defense MIL standards, 13VV, 55V. And these debug agent allow you to, debug your BSP, kernel, and internally, certain other portions. So what host packages are also called as HSP, host support package. And the target related stuff is called as BSP, board support packages. Host support means the ones which you have to install on your Windows operating system or Mac or any Linux machine, desktop kind of a system. These tools together in an IDE, like if you install an IDE, you'll have an awesome compiler, debugger, interpreter shell, system browser, object browse, logic analyzer, certain third-party tools, some runtime environment from language, all combined together for communication, guys. An IDE view, you can think like this is what it looks like. And there are some huge advancement in the tool 3, like you have dynamic link load of the features, OS configuration changing, debugging capability, and a lot of system visualization analysis can be done, which was lagging in the previous ones. These are some different platforms people may look at, like if you're looking for VxWorks core OS and file system, IO subsystem, and driver management. Only kernel means you should look for multi-core SMP or AMP, advanced multi-processing, task with process control, interrupt exception handling, timers, right? Like that. So MILS platform and 653 platform are two different strong platforms. Like 653 and all is used for aerospace defense and all. Well tested. You can think of a development tool and real-time system on a network backbone to talk to each other. These are some, it may be too much to say that you should mug up all this. I'm just giving you a view, guys, that if you were to work on product like VxWorks, this could be one. Tomorrow, if you have QNX, they'll give you Momentix ID, then different optimized GNU, Renesas hardware. So it will keep changing. But be aware that everybody will have these tools for launching some tools, some shells, some browsers, some project facility. and so and so. And mechanism via which you can customize your real-time systems. Like you can add certain file system or drivers or network stack or remove them or add some memory management partitions, include or exclude them, right? One of the best part of the VxWorks computing platform is that every application or task resides in a common address space. It's very, very fast, one single image. But only the problem with this is it's a hub kind of a problem. They say there's a saying, hub gaya to sab gaya, because on a hub, everything is connected. So if somebody else has done a mistake, everybody will be crying on that. So that's why nowadays, if it is not a very simple system, control systems, they prefer using MMU based architecture where, every process has its own address space. So there is a kernel mode, dual partition kind of a thing. So kernel privileged program will be running separately and the application program will be running separately. But it also has to be at the cost of context switching, mode switching, and so on. That has to be, very much understood. Another view of as if you are sitting in the lab connected to a target board. Tornado host is running, RS-232 is connected to VxWorks target on a backbone on Ethernet. And a lot of things get supported. Usually they used to ship CD-ROM. Now everything is licensed, paper license. You can download them. Okay. HSP host support package followed by generic VxWorks kernel, certain architecture on which it will run, and the board related drivers and IO is what they provide you with certain agent for communications. If you were to program on, Tornado, these slides will make sense. Otherwise, you can just skip them as of now. Just keep in mind that, this is a Windows-based installer. So in SQL and Tornado, user Tornado will have these directory structure. So it's very nicely documented. One of the best part of VxWorks is one of the most dominant operating system of the world in real time. See, this is host related stuff, setup related files, shared files for the targets, specific files, some basic documents for help and all. So very well maintained. If you have to go and include, I think I'm just trying to tell you that these are some things which will make only sense when you have a project on VxWorks coming up. Otherwise, we'll end up putting a lot of energy, but all in vain. And being so costly that it is only in certain projects being used. If you're using in Lockheed Martin, you're using this, or aerospace, Boeing, Bombardier. These are someone like where hard real-time operating systems, UFO-based unmanned mission like NASA, JAXA, STEX, AI-based systems, even ISRO, DRDO, LRD. These kind of system uses VxWorks. So the conclusion, guys, are that RTOS is a very scaled down general purpose operating system and provides us worst case response time, including failure. Homegrown real-time OSs are good, means you can decide and design your own real-time OS, but it suffers from a lot of problems. One of the very core problem is that you need to keep training the people. So if suppose I and you all 5 to 10 people combine together, build an OS, as long as we are there in this organization, we'll understand, right? Once we are off, how will somebody understand that code? It's a very huge problem. Okay. Better choice is that always, commercial off the shelf stuff. You can also see microkernel is more preferred in this particular design. So I think for today, we have reached to the extremely brief and brisk introduction to the consumption knowledge of real-time operating system. So our course does not wants to hard code a particular operating system at this moment, because we are not sure, right, that what kind of a work tomorrow you may get in with, right? So that being the case, we will keep the today's session over here. Just wanted to, I think, track. Where it is. Yeah, there we go. Just trying to keep a track where we are. Yeah. So I think we are through with this all, guys. Let's go to this. Going. Isn't it? So this is where we are progressing. I hope it's getting completed soon. I like to format it here. So we have these many sessions left yet over here. These many here. These many here. I'm just trying to connect it here and finish it off. And as well as here. Let's keep changing these, marking these colors as we progress on an everyday basis. Any queries?